Alright, we're good. I think we're live.
Dokes.
Yep, we're live.
Well, apologies for the technical difficulties, and hello everyone. Welcome to today's brand new episode of Corecast. I am your host, Tim.
And I'm Mikey.
And this is Sile. Welcome, everybody, to a brand new, exciting episode of Courtcast. Before we begin, a few logistical things. If you haven't already, do join our Discord channel. And if you're watching this on YouTube, where we do this or try to do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode, and we'll get to them. So without further ado, let's get to it. So last episode we had talked about essentially the energy of vacuum and that it's not just all empty space. And so and this leads to some interesting consequences that we'll discuss today about the universe expanding and whatnot. Before we get to it, I guess Tim or Mikey, whoever you feel is better to answer this question, maybe we can give a history of like kind of how people thought the universe evolved, some like basic history on that, just kind of lay the groundwork.
Yeah,
Yeah, okay. So I guess the interesting story is wait, there was that guy who, like a really long time ago, who um he kind of figured out that the universe had a finite size because if the universe was infinite, right, then you would see like there would be no dark spots, right? You'd see stars, there'd be no space between stars because there'd be some
yeah.
other star there really
I
far away.
I think it started. I think the beginning. I think you're referring to this really naive question, like a kid could ask, be like, how come the night sky is dark, right? And the idea is, oh, maybe it seems so obvious. Oh, the night sky is dark. Why is that a big deal? But if you imagine if the universe was a finite size and there are light bulbs everywhere, and you know that light has a finite speed, if you wait an eternity, eventually the even if it was really far away, will reach you, and it's gonna bounce back and forth, to the edges of the room, and it's gonna light up the entire night sky. Basically, the night sky will be lit up by stars that are really far away. All their light would light up. But that does not turn out to be the case because night sky is dark. Stars are very dim, and that's a hint that the universe actually was not static. There was a time, before which there was no light, so that the light could not fill the universe. So that was one of the hint that says that the universe must be expanding, I think. But I don't remember who came up with
No,
that.
no, no, not that it's expanding. If you assume that time is infinite in the past and that the universe is infinite in space, if you assume those two things, then you get this result logically that there should be no dark spots in the sky
Right, yeah.
because uh,
So I think because night sky is dark, that means so you can draw some logical conclusion. That means there's gotta be a beginning, and if you assume that the beginning is small, which we believe to be the case, then the universe must be expanding. And I think, because small to large, right? And then I think that statements like these became more concrete once Einstein came up with the Einstein equations that governs the structure of the large universe. And in those equations, you can see that those equations can naturally accommodate kind of three possibilities. Either the universe has always been stable, it's not changing, it's not getting larger or smaller, or the universe is getting smaller, or the universe is getting larger. It's three possibilities. These are logical possibilities. And these are governed by kind of the terms in the equation, basically. So I would say that's kind of the beginning of cosmology, really, when Einstein wrote down the Einstein's field equation, and people realized that, hey, you can apply this to the entire shape of the universe. And then the question immediately came up, like, well, is the universe getting bigger, smaller, or staying the same? Right.
yeah. So I mean, maybe like that was it's I guess just wanted to go back a little bit because it wasn't obvious to people that the universe was expanding at all, right? Like if you go back to like religious times, the Bible says that God created the universe. Okay, that means kind of implies that people always kind of believe that there was a beginning to it. But I can't back this up, but I do think there was a strong bias to believe um, that the universe was static, that it was not getting bigger or smaller. It just was what it was. And some listeners might have heard people talk about this as like Einstein's biggest blunder, where Einstein himself was very, very like almost religiously devoted to the idea that the universe was static, that its shape and size was not changing with time, even though his equations sort of implied that it should be either growing or shrinking, that a universe that's static is kind of unnatural. It's like kind of like balancing a pin on its tip.
That them that's interesting. So I guess few things. I want to kind of double click onto what does expanding mean? So when you say the word expanding, like yeah, just what does that mean for starters at the most basic level? How do I think about that? I'll put that question over to Mikey since you look like you're about to answer and I want to beat you to it.
Yeah, I was just trying to think about whether or not I should talk about like what people like. There's many different ways you could think about
Hmm.
the universe expanding, right? You can imagine that the universe is a box full of stuff, and the boundaries of the box are just getting bigger. That's one, but that's not what physicists typically think of when they describe the expanding universe, and it's also not um, the picture that Einstein's theory tells us about the universe expanding. In the context of modern physics, when we say the universe is expanding, we mean that space is actually stretching. Like if we could think of space as like a fabric, and all of like the planets and stars and people are kind of like painted on this fabric, and literally this fabric, if you imagine it like a rubber sheet, is just expanding in every direction.
Hmm. I so actually that seems to kind of play devil's advocate based on my everyday experience, like that seems really strange. Like I don't see that like on Earth, I don't see like if I stand next to you, I don't see like you moving like away from me if we're both staying stationary. So like why don't I see that?
Yeah, and
Yeah.
I think that has to do with the weakness of gravity. Gravity is a very weak force. I mean, sure, space is stretching, but you can also interpret it alternative as kind of like a force that's pushing things away. If you think of it this way, um, the force that causes things to push away because of the expansion of the universe is tiny, tiny. And the force between electrons and atoms, those forces are way larger. So if you imagine an atom, let's say the space between the electrons and nucleus is getting a slightly tiny bit larger because of this stretching of space. That's immediately compensated by the attractive force of the electromagnetism, which just pull the electron closer. So you're never going to see that. Um, and in fact, gravity itself will shield you away from this. What I mean is like the solar system. It's probably more or less immune to this effect, right? Like the space between the Earth and the Sun might get a little stretched out, but the Earth is somewhat attracted to the Sun, and that will get compensated. So what we're really referring to, the creations of space, is between some of the largest void in the universe, like between galaxies. There's so much nothingness, close to vacuum, and everywhere in those void, space is getting created, and there's nothing to counteract it in some sense. So this is what we mean when we say universe is really getting expanded. It's these vast void area that are unimaginably big, that are getting bigger and bigger and bigger.
Yeah, it's kind of
Wh-
tricky though. We shouldn't say that it's because of the weakness of gravity, right? Because, in some sense, the strength of gravity is counteracting this effect in this like in the way that you said, right? Like so, you might imagine that if space was stretching extremely fast, I literally might be pulled away from the earth. Like I could jump and the space between my feet and the earth would stretch and that would pull me away. Um, but actually, the attractive gravitational force between me and the Earth is enough, as Tim said, to counteract the stretching of space. Um, the reason we only see this on super large distance scale is because the force of gravity becomes much weaker, as some of you may know, as distances of objects get further and further away. So when we're talking about the stretching of space, it's stretching ever so slightly that you only notice it, on the largest distance scales where the force of gravitational attraction is very weak.
Mm, that makes sense. I mean, that makes sense at least from the way you described it. I guess like if I'm a skeptic, how do we know that this is happening? Like you're telling me this is happening, but like what experiments have been done or how are experiments typically done to like validate this?
Yeah, I think there are a variety of ways. I think that this probably the simplest to understand is to see light from this very very distant galaxy to see how they modify, because the majority of the stretching occurs through these void areas in our universe. So in order to detect these effects, you kind of have to look at things that passes through these void areas. And what that is light. So if you have light coming from very distant galaxies, and through eons, it has traveled through these void. So for a long, long time, the because light travels through space, and as the space stretch, the light also gets stretched away. So the color of these light will change, right? But we know that, for example, if let's say a distant galaxy has a lot of hydrogen, we know what the color of those light is supposed to be, and if it gets stretched out, we know how much stretching has happened. So this is one example that we can see
Totally
that.
forgot about that example when we talked about this last week.
Yeah, I mean, so that's one very simple example where you can see like, hey, look, looks like the light has stretched, so the universe must be expanding, and there are a variety of ways, mostly I think involving stretching of light, and you can also see how light sometimes get absorbed, and I think those you can also make an inference. But there are a variety of ways to this game of like how things are stretching. Then you can gauge, kind of directly measure how much the universe is expanding.
Mhm. I guess Tim, I'll pose the question to you that I posed to Mikey last episode, just to gauge your answer to it. Like, how do you know that this isn't like a fifth force that's like the anti-gravity force, like a repulsive analog of gravity. So instead of attraction, it's just repulsing everything, but it only works on like very, very large distance scales.
And in some sense, I mean, in some sense, it's sort of what you described. There is this repulsive gravitational force that acts on large distance. I mean, it pretty much is what it pretty much is what it is.
Oh,
And of course, you can argue, how do we deal with that? What is the most natural thing to do? Just, I mean, it's a conundrum, right? The observational fact is that there are these large scale effects of gravity that's making things, pushing things away in some sense.
mm,
Um, and and I think, I believe, Doc, and the stretching of space time has never been observed locally, like in a small lab, because it's too weak, way too weak to observe. I
mhm,
believe that's true. Um, so yeah, it's literally as you described, and there are multiple ways you can go about it. You can say, hey, maybe Einstein was wrong. We toss Einstein's equation away. But then, if Einstein's equation was wrong, you will see other effects. You wouldn't just see large scale changes, right? So
mhm,
I'm not saying that's not possible explanation, but the most natural explanation is just say, hey, Einstein was mostly right, but Einstein had this modification we call the cosmological constant that really could accommodate this effect, this stretching of space-time. So that's like I would say the most compelling
mhm.
explanation, and that's what
Ye-
the scientific consensus is right now.
No, but he did
So,
ask though, how do you know that it's not a fifth force? Like how do you know that it's not something completely separate from Einstein's equation
Oh
and
yeah,
gravitational effects and everything?
y-
yeah.
yeah, let me add something to that. Like, that it's not the stretching of space time. It's space time is like fixed in, I don't know, in size or whatever you want to call it. And things are just not moving away from each other within that space of fixed size.
Well, that wouldn't explain the stretching of light, right? That's really a crucial one. Like if you
Hmm.
imagine light as a wave,
Hmm.
uh, and a smaller wavelength wave is blue, and larger wavelength waves are more reddish.
Hmm.
We can literally see that faraway objects look redder than closer
Hmm.
objects And so that's yeah, that's one of the. I think that's probably the biggest piece of evidence. But I should mention there are a bunch of folks at Dartmouth University who subscribe to this idea that goes by the name of quintessence, where they try to imagine that maybe it's not a gravitational effect. Maybe there's some mysterious extra thing that's causing the universe to expand. But those theories run into all kinds of problems when you try to combine them with early universe
Yeah,
cosmology and really hard. Yeah.
yeah. I would say Sahil. I mean, like perhaps you could argue that maybe distant galaxies are a little different. Their hydrogen is a little different. Physics is a little different. But that violate one of the central principle of the universe because we believe that our location in the universe is not unique. So if you were to say somehow we are kind of the center of the universe and everything around us, the further away they are from us, somehow they're different. That's a very strange proposition. So people don't like that. And of course, you also have to say, well, how the heck? Why is hydrogen different in different places? And that's really awkward. I mean, it's maybe you can cook something up that's sensible, but that's very not palatable scientifically.
Yeah, you really have to jump through a lot of hoops
Yeah.
and bend over backwards to try to make this work. Whereas if you just assume that Einstein's theory is roughly true, then you get everything for free. So it's just a simpler, more economical explanation.
That's a fair enough. Fair enough. So I guess like coming to this, what do we know about this expansion? Actually, Tim, I want to pose another question to you that I asked Mikey in the previous episode. What is the space expanding? If the universe is expanding, what is it expanding into something, or is it just like how can one think about that? Like, yeah, is there like a greater thing that's expanding into, or is it just like it is like the thing itself, and it's just creating something out of nothing in some sense?
Yeah, I think I mean it is kind of hard to think about, but from the particle physics lens, one could think of space-time as some kind of a substance. Space-time itself is a field that we mentioned, just like the electron field, the electromagnetic field. You can think of it this way. And if we do believe that's true, then it means that it's kind of like a substrate that everything lives on. And this substrate is getting stretched out. So the stuff that is getting bigger is this space-time field. So I think that's probably the most reasonable way to visualize it.
And when you say field, can the audience think of it kind of like an ocean of like waves in some sense, just to
kind
give the
of.
analogy what a field is?
I think that's a fair analogy. I can't think of a better one. I mean, it's not perfect. I can't think of a better one.
Of course.
Yeah, but of course, like in theories like string theory, we believe space-time field itself is made of something else. But then I don't even know how to think about that anymore. So
That's fair. That's fair. Okay, so kind of taking a step back, we have this notion the universe is expanding. Is the rate of expansion constant, going up, going down? Can you walk me through like the history of like from the early universe to like now and what we're seeing in terms of how it's been expanding, if it
Wait,
has
sorry.
been expanding?
Can
Yeah.
we put a pin on that for a second? Because I just I wanted to revise my answer from last week when you asked me what the
Yes.
universe is expanding into.
Oh yes, go for it.
Of course, my answer last week was I have no idea. But I just wanted to point out that like it seems like a very important question, right? Because like let's imagine that I have a sphere here, and the sphere is getting bigger. Well, that sphere lives in this, the bigger space that is my room. So you could say that the sphere is expanding into the room, right?
Mhm.
But it turns out mathematically, in mathematics we call that an embedding. So the sphere is kind of embedded in the room, and it's expanding into the room. But you actually don't need, it's not a necessary thing to require. You can describe a sphere without any reference to a space that it's embedded into. So you can just describe a sphere and it's expanding, and it's mathematically perfectly okay to say that it's not expanding into anything. It's just all that exists and it's getting bigger. It's very counterintuitive because all the spheres that we know of are embedded in our three-dimensional space, but
Mhm.
mathematically it's just fine. And I think that's why physicists don't really tackle that question, or see it as like importance. One, because it's like very difficult to answer, and two, because it doesn't really require an explanation.
Makes sense. Makes sense. I appreciate your revision of your answer from last week. Yeah. So coming back to the question I asked before, about like the rate of expansion, like how would you kind of describe it from like kind of the evolution of it? Has it remained constant, gone up, decreased? Like kind of walk me through the early universe. Give me kind of a picture of the story of it.
So that this is a very good question, and I think initially when people realize that the universe is expanding, that's a very natural follow-up question. Is it expanding faster or is it expanding slower? Actually, the very natural answer is that it should slow down a little bit. If you believe that the expansion of the universe is caused by, let's say, the Big Bang, because the universe used to be small and it got big really fast. And you could imagine if that were to happen, like kind of like a bomb go off. It's not a good analogy, but okay. But imagine like a bomb go off. You would imagine at some point, kind of the power of the bomb will kind of fizzle out a little bit. Like the explosiveness will kind of slow down. That's what you might expect for the universe. It's in the beginning, it's really getting big. It should fizzle out a little bit because gravity attracts, so that explosiveness will kind of decrease. So naturally, we expect the expansion rate to slow down. In fact, that's what we observe using data in the early universe, right? It was expanding and it slowed down a little bit. But what's intriguing is that recently, in the most recent history of the universe, that slowdown has kind of gone backward. It started to accelerate back again. And now that's the intriguing story. That's a little bit unexpected. But it turns out that to accommodate that, Einstein's blunder, the cosmological constant, the extra term in the equation, actually allows that to happen. And that was, I think, one of the Nobel Prize is to confirming that indeed that term exists, that, the accelerated expansion of the universe is not explained by anything else but this extra piece, this extra ugliness in the equation that allows it to kind of, not only to expand, but to expand in an accelerated way, faster and faster and faster and faster.
Before we go further on that, I had the question. I lost it in my mind. There's something you said that I wanted to hone in on. Okay, it's lost. I lost my train of thought. So okay, so it's accelerated expansion. Oh, can you give like kind of ballpark, not precise, but super ballpark, like timings of what do you mean by early universe? What do you mean by now, recently? Like, is it last week that we saw it like expand the accelerated expansion suddenly, or like how gradual is this?
I don't know the numbers, Mikey. I think it's like between 0 second and like at least 0 second to 1 minute. The acceleration is definitely slowing down, and then maybe to 10,000 years. Also, probably longer than that. Maybe even a million.
No, the acceleration started very recently in cosmic history, right? Like,
Yeah,
so the universe is 13.6 billion. Yeah.
Yeah, I'm saying the slowdown. Initially, it's really slowing down, and at some point it turns over. The slowing down in the beginning is that just what happens, right? The universe got really big quickly and kind of slow down. But my question is, when did it happen to pick back up again? I think that's recent, right? Almost like now, basically like now.
Some people think it's like a real coincidence that we just happen to be alive so close to the time that the universe started accelerating again. So for most of the history of the universe, the expansion was slowing down. I'm just gonna take a stab, just take a guess at it. I bet it's like a couple billion years. The universe is 13.6 billion years old. And in cosmic time, a billion or 2 billion is very, very recent.
Yeah.
So I would guess that around then is when this acceleration started to kick in.
Yeah.
Gotcha. Oh, go.
Yeah, but it's also important to note that this acceleration is very tiny for now, right? This turnover, right? Between slow, it was slowing down, and then not slowing down anymore, and just picks up this tiniest bit. And of course, if you project it in the future, in the really, really far future, this expansion is going to dominate. The universe is going to be like, boom, just really in many, many eons down the road. But just the tiniest little bit of a tilt accelerating. It's really hard to explain. Let me just put it that way. It's a fact, but we don't really know why.
I think we know.
I wanted to ask a question about, like, do we understand the mechanism behind this? Like, why is this happening? Like, more in recent times.
Yeah, I think there's the conventional story. I can go for that. So the conventional story is if you believe that this is caused by the extra term in Einstein's equation called the cosmological constant, it really is just there's a bunch of equations and there's just an extra number that isn't attached to anything, right? And if you believe that to be true, this dangling number, because it's not attached to anything, and because gravity is universal, it sees everything. So the only thing gravity sees, like the only thing this number will interact with is gravity, basically. It's just this extra term in the equation, and the only thing it picks up, it interacts with is gravity. Okay, if you believe that to be true, then we can go to particle physics to find an answer. What is that one extra number dangling in our equations in particle physics, in quantum field theory? And that one number is what Mikey described in the previous episode. That's the vacuum energy, turns out. And it's very reasonable because, like, the majority of the expansion of the universe is caused by the void in our universe, which is when there's nothing. So it's very reasonable. But if you do a calculation, if you try to estimate what that number is, it's way off, right? That number should have been like really, really large, like trillion. But when you measure it, it's tiny, like 0.00, I don't know, 10 to the negative 19 or something. Super tiny, right? So, but this is the conventional explanation. We believe that the cause of this expansion is the extra term in our equation. We call it the cosmological constant, and we believe that to be the same as the vacuum energy. And it happens to be very small. So that's it. That's the conventional explanation.
Just to unpack that a little bit, because Tim has been talking about this mysterious term in Einstein's equation. And really what that term describes is energy in space that does not dilute as the space expands. So normally if you have regular material or some regular substance filling like a sphere, for example, as you increase the size of the sphere, the density of that material inside will go down, right? It will dilute. But there's a term in Einstein's equation that essentially represents some substance that doesn't dilute as the space expands. As the space expands, you're actually creating more of this energy. And that also is an explanation for why this causes an accelerated expansion, because if this energy is causing space to expand, as space expands, you're creating more of that energy. It's driving further expansion of space, and that's why it has this characteristic of accelerating the expansion.
So there's like a positive feedback loop built into this.
Yeah.
Is what I'm hearing.
Yeah,
And what you're saying is that this kind of weird substance that doesn't dilute as space stretches is exactly something that particle physics or quantum mechanics kind of predicts should exist. Of course, it predicts that there should be much more of it than we actually observe, but it does predict that something like that should exist.
Yeah, and I just want to add one thing, that like this term, this extra dangling term that doesn't do anything, is very strange in the equation. Because in particle physics, most of the time, usually in experiment, what we see is difference in energy, right? Like if you reduce the energy of the system by a little bit, maybe you could create heat or something. Or like if you're familiar with electrical outlets, right? If you're an electrician, you see that only the difference in the potential is a physical observable. Like birds on a power line, they don't get electrocuted until they touch the ground, right? So in physics, a lot of times you look at differences in energy. So you never just see a raw number with nothing. You always see the difference between two numbers, and that's what's physically observable. But what's strange about gravity is that gravity sees everything. It sees the absolute number. It doesn't just see the difference. It just sees the absolute raw energy in the vacuum. And that's why it's so strange. And that's why Einstein really didn't like it in the beginning, I think. It's, I would think that if you talk to most physicists, they'll be like, this is an ugly term. But yet, it's there.
Mm-hmm. Gotcha. Okay, one last question for you. I realize we're almost at time. Is is it possible for the universe to slow down in expansion like much later on? Like, is this definitively for sure that's just gonna have an accelerated expansion? How should I think about that?
I would say it's impossible. I mean, if you just take what we have in the universe so far, just
Hmm.
like the material, the substances that we see in the universe so far, um, all of the laws of physics essentially predict this behavior of like expansion, slowing down, and then eventually turning around. In order for something to suddenly cause it to turn back around yet again,
Hmm.
that would require something very drastic, like a bunch of like material would have to spontaneously appear out of nowhere in order for that to happen, or the laws of physics would have to spontaneously change drastically at some point in the distant future. So I'd say it's a pretty safe bet that this acceleration is going to continue.
Yeah, I mean, I mean, I guess there's two questions, right? Like, oh, is it possible? Of course, it's possible. Nature does whatever it wants, right? But if it does happen, we'll be pretty darn surprised. Like that means Einstein was wrong. That means that because if it's a cosmological constant, this dangling term would not just disappear. It will always be there today, tomorrow, 1,000 years, and a bajillion years. It will always be there. But if it turns around, it means that this is not a dangling constant term anymore. It's not like a nagging imperfection of the equations anymore. It means that that term can change. But I would imagine that even if it were to change, we're not going to see it in our human lifetimes, right? Maybe in another billion years. But like we're not going to be there to see it. So the bet is probably even if we were to change, we're not going to see it. So probably not. Like we're not going to see it change basically.
That's fair. So there's an audience member question that I want to ask, and then we can adjourn. Isn't the universe possibly 2x older for James Webb discovery of distant mature galaxies? I don't know if any of you happen to know the answer to
No.
that.
I don't know the technical details, but I heard that this guy, so yeah, James Webb telescope saw some galaxies that are supposedly older than they should be according to kind of people's models for how galaxies form. And
Uh-huh.
so pretty much this one person tried to build an entire theory off of this one observation for why the universe is older than we think. But
Hmm.
um, there's just so many pieces of evidence that point towards one answer, and there's just this one thing that's a little bit off. Um, and so people, as they do, will make theories to try to explain this one observation, but it's not going to align with everything else. It's probably more likely that uh, models for how galaxies evolve are slightly off or slightly different from what we imagined.
Mm.
I don't know. What do you think, Tim?
I haven't dug too deep into it, but yeah, definitely the age of the universe isn't just calculated by one single telescope, right? There's there's multiple data points checking at the expansion rate of the universe. They get consistent answer and they make an inference backward. So it seems like 2x is yeah. I would still maintain that it's the consensus is roughly 13 billion years. Maybe it could be modified slightly, but I doubt it's going to be 2x. You know.
Mm. Gotcha. So, is there any last parting thoughts that you wish to impart to the audience, or I don't know, yeah, uh, before we head out?
I can try to summarize. So unfortunately, we really don't have an answer for this question why universe is expanding, and some some physicists, maybe not physicists, but some people might feel like, oh, we can blame it on the cosmological constant. Somehow that explains that expanding. It doesn't really do a job. It's more like a parameterization of the problem, and kind of similar to dark matter in some ways. We know there's something there. There's this, we call this dark energy. It caused the universe to expand, and maybe it will do a bunch of funny things. But the real answer is we don't know. We really just parameterize it. And then that's why the cosmological model right now is called lambda CDM. And it stands for lambda cold dark matter. Lambda is just a number for the dark energy. And there's literally no explanation on what it is. It really is just, we just blame it on a number. So, but it's a deep mystery that remains to be figured out, I guess. But I don't know if you will find an answer in our lifetime, unfortunately. But intriguing mystery.
I would just end by saying that I'm really glad that we're alive now and not, you know, trillions of years in the future, because as the universe expands, all the stars will move away and the night sky will become truly dark. So even though we have these mysteries about what's causing the universe to expand, at least we have those mysteries or those questions to ask. Civilizations, you know, trillions of years from now, won't even have any awareness of anything outside of whatever planet they happen to be living on. So it's a good time to be alive.
I like that. I like that. Well, on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah. See you all next week.
See ya.
Bye bye.
That was really good in terms of like